Okay, I gotta record this lecture because I couldn't get anything to work yesterday, so bear with me. All right, so we stopped on this one, and I think we already do have a lot of these written down. I just wanted to kind of go over it again, even yesterday. So these beta values, like this 1 and this 1/2, if you refer back to table 8.1, so I'm going to go to that really quick and kind of show you what I mean. Well, this isn't table 8.1, but it has a few of them. So like if you've got a hoop or a disc, remember it's like that 1/2, or there's no number in front. For a solid sphere, it's 2/5, and then 2/3 for a hollow sphere. So if you go back to these betas, I think I was here, yeah. So here it's got a disc as 1/2, the solid sphere is 2/5, and so those numbers are just the same as they are in that table. All right, so what we had written here was like the total kinetic energy was translational plus rotational. So translational, if you remember, is 1/2 mv squared, and rotational is 1/2 IW squared. Okay, so this doesn't change. It's always that. But this one, it's dependent on that. So what I mean is whatever that beta is, and that's based on whatever shape the object is. mr squared times that w squared. Now, remember that velocity is angular velocity times radius. So if we rearrange that and solve for angular velocity, then it's v over r. So I'm going to take that right there and plug it in to that angular velocity. So you've got 1/2 b mr squared, and then you've got vr squared. Well, look what happens. I just keep writing this one all the way through. So you've got b mr squared, and then you got to square both of these, okay? So you got v squared over r squared. Well, what happens to the r squared? It cancels. So you have 1/2 mv squared plus 1/2 bmv squared. Well, look, if you take that b and you put it out in front, it's like these two equations are the exact same, okay? So you could say that rotational kinetic energy is just beta times translational kinetic energy, because this is the beta and this is the same thing as translational, okay? So and then you could just say, you could say the total is 1 plus beta times k translational. So if you factored that out, it would be this equation. See, because if you took translational is 1/2 mv squared. So if you're multiplying by 1, that's what that is. And then if you multiply that by beta, that becomes this equation right there. Okay, so hopefully that makes sense. I kind of wanted to reiterate that yesterday. Okay, so now for this one. This is solid versus hollow shell, and it doesn't give any numbers or anything, and I don't particularly like it when they do that, but you know, it's okay.
It just wants you to figure out which one is moving faster when it reaches the bottom of the hill. And so it goes back to that sort of moment of inertia, which beta it has. Okay, so I'm going to play that so it actually is bigger. Now, if you think about this ramp, it has a height. So before these balls roll down the ramp, do they have any kind of potential energy? Well, absolutely. They have gravitational potential energy. They have mass, they have gravity, and there's height involved. Okay, so you do mass times gravity times height is equal to the kinetic energy translational plus the kinetic energy rotational. Okay. Well, we know that the total is like 1 plus beta times translational. That's this right here. We figured that out on the stuff before. You could rewrite it if you wanted to be like 1 plus beta 1/2 mv squared. Okay? And that's all equal to this mgh. So if you went to solve for velocity here, then you would have velocity is equal to the square root of 2 times gravity times h over 1 plus b. So all I did was multiplied both sides by 2 to get rid of that half, divided by m, which canceled that out, and then also divided by 1 plus beta to both sides. And that left v by itself. Oh, and then of course you have to do the square root because it's squared. Okay, so we're comparing the velocity of the solid sphere with the hollow sphere. So we'll call the solid sphere 1, and we'll call the hollow one 2. Okay, so if we're comparing them, then that means that we got to do a ratio. So a ratio is just dividing them. So you have 2gh over 1 plus b divided by 2gh over 1 plus b. Well, now you got fractions, and no one likes that. So you got to multiply by the reciprocal. So you got to do, I put B2 for both of them. This is B, if you were wondering why I did that. That was a mistake. I know you can't imagine that. So that was a joke. All right, so when you do that, what's going to happen to your 2gh? It's going to cancel on actually both. So you're going to be left with v1 over v2 is equal to the square root of 1 plus b2 divided by 1 plus b1. Well, then you just have to go through and figure out what the beta is. So for a solid sphere, for a hollow sphere, it's 2/3, because this was beta 2, okay? Beta 2 is the hollow one. Beta 1 was the solid one. And the solid one is 2/5. So when you go through and do that, it shows that it's got like this 1.091 number, which, because it's over that 1, it's showing that it's greater than, and it's going to be faster than that hollow sphere. So there were no numbers, but you could kind of break it all down to where you're just working with that beta number. And it just shows you that it's 1.091 faster than the hollow one. Okay? All right, so that was example 8.12. Then we get into this idea of accelerating acceleration of rolling objects that are on like an incline. And if you remember, whenever we had an incline, we had like a normal force and then we had a frictional force. Okay, so this is like in the y direction, this is like in the x direction. Obviously, if it's rolling, it's going to have acceleration, right? It's going to be going in the x direction as well, but opposite of the frictional force. But then remember too that gravity is pulling straight down no matter what. Okay, so the frictional force, because torque is, remember, torque is force times distance. Well, a friction is a force. So it's like torque is equal to this static friction. I didn't mean to go so crazy with my F there. I know my writing messes with you guys sometimes. There. Friction times radius. Okay? And the R in the situation is the ball's radius. Okay, so we're going to calculate one. And again, it doesn't give us any numbers or anything. It's just kind of, we're trying to figure out what the acceleration is. And what happens is things start to cancel out, sort of like they did in that last example. All right, it's kind of a lot though. It's kind of a lot of writing. So I had to write in the margins on some of it. I can see you guys rolling your eyes at this point. So the sum of torque is equal to that R times friction. And then we also had an equation a couple slides back where acceleration or angular acceleration was equal to torque divided by moment of inertia. This one comes from, like I said, a couple of slides ago, I think, where torque was equal to moment of inertia times angular acceleration. I just solved for that one there. And if you go through and break this down a little bit farther, torque is radius times friction. Okay, so there's that. And then we also need to remember that like translational or linear acceleration is equal to angular acceleration times radius. Okay, those are all things that we kind of have to keep in mind. All right, so now go to the other slide and we can start breaking this down a little bit. So we're doing the sum of the sum of forces in the x direction. So we've got our mass times gravity. Now, let me go back to this picture for a minute. Okay. See how this hangs down like this? Well, that has some x component to it. All right, so it's this angle right here makes up this angle right here. Well, when you take the opposite of that, that's the sine. All right, so it's mass times gravity sine theta minus friction, because friction's going backwards, is equal to mass times acceleration. So force, remember Newton's second law, mass times acceleration. All right, hopefully you guys are with me at this point still. Mass times gravity sine theta. If I go back to this equation and solve for friction, so I'm multiplying angular acceleration times moment of inertia over here, dividing by radius to solve for friction. Okay, so minus like that. Okay, now also remember back on this one that I wrote this out. Well, if I rearrange it to solve for angular acceleration, I have linear acceleration divided by radius. Okay, so I'm going to plug that one into this right here. So when you do that, you have this. Okay, so now what I'm going to do is I'm going to add that over to the other side. So mass times gravity sine theta is equal to mass times acceleration plus, and keep in mind, we're trying to solve for acceleration here. Like, that's our goal. Okay, so I'm going to try to get rid of this denominator. So I'm going to multiply both sides by radius squared. So I have radius squared times mass times gravity sine theta is equal to mass times acceleration plus moment of inertia times acceleration. Okay, now I gotta break it down a little bit more, unfortunately. Okay, so that stays the same. If I pull acceleration out like that, I could do that. Now, still got to keep going because you've got mass plus, you got to remember what the moment of inertia is. The moment of inertia is for a solid sphere or solid ball. That's what it said in the explanation of it. So that's 2/5 mr squared. Well, now I have two m's, so what can I do? I can pull an m out. So you talk about algebra. We're doing some algebra here lately, right? All right, so I could distribute that and it would be fine. Okay, now I've got to solve just for acceleration. So I'm going to divide by m 1 plus 2/5 r squared. Okay, so what happens is your r squared is going to cancel, your mass is going to cancel, this cancels all of that, and you're going to be left with acceleration is equal to gravity sine theta over 1 plus 2/5. Okay, well, one, if you were going to make it into a fraction so that you could add the 2/5, you could do 5/5 plus 2/5, which would give you 7/5. I don't like to have a fraction in the denominator. So you're going to multiply by the reciprocal. So acceleration equals gravity sine theta 5/7. Okay. Whew, that was a long one. I know. I gotta stop this recording though because YouTube only lets me have so long of videos, and I'll start another one.